recording. Fine. So welcome back. For the plan for today, today's lecture is to introduce you to a different architecture for model-free learning, which broadly goes under the name of policy gradient methods. Okay, so we will see in a second what these are about, and all the different flavors they come with. For tomorrow, we will discuss multi-agent reinforcement learning, and we will try to see how model-free approaches can be extended to the situation where there are many agents which pursue, each agent pursues its own goal. So these two lectures, in a sense, come together because, as we will see tomorrow, these policy gradient methods in one particular flavor actually make a connection with the game theory, and therefore this will be the overarching concept that connects the policy gradient methods with known approaches to game theory, such as evolutionary game theory. But first things first, so let's start with the policy gradient methods. So what is the key idea here? So far we've been mostly discussing approaches which are based on action value methods. So action value methods are methods which are essentially based on the knowledge of the value function, or the state action value function, Q. So in short, the idea is that everything is centered around some possibly approximated form of your Q function. Okay, and from that, you derive a policy through epsilon greedy, or to, so for instance, just to fix the ideas, through epsilon greedy, we derive some policy by AS, which of course implicitly depends on the parameters of your approximation. This class of methods are also called critic only, in the sense again that the important notion is to evaluate the Q function or the value function, and this is what the critic does. Okay, the critic is a sort of a conceptual description of any kind of algorithm that is able to evaluate a policy. Okay, so you have a policy, you evaluate it, and then you construct an approximation starting from your new evaluation. Okay, so the role of the critic is central. So if we have to diagrammatically explain what this does, so you remember the usual environment agent interface. So this is the environment and this is the agent. So there are actions, and then here the agent receives information in the form of percepts, which include rewards. And so what does the agent do? So in particular, for instance, in temporal difference learning, these percepts might be rewards and states. Okay, more generally, these are just observations of the states, but let's assume that these are the states themselves. So starting from these percepts, there is inside the agent, there is a part of the brain, so to speak, which is called the critic, which receives this information, constructs the temporal difference error, okay, and feeds it into itself. Okay, so from the critic has in its belly this knowledge of an estimate of the value function, receives new information in the form of rewards and new states, and updates, constructs the temporal difference error, and updates the previous estimation of the value function. Okay, so this cycle here that I'm depicting here means that there was an estimate of Q, then new information is received in terms of new rewards, new states, which is used to update your Q function by means of the temporal difference error. And only after that, then the critic produces a policy. Okay, which is then turned into actions and so on and so forth. Okay, so you see that everything circles around this notion of the critic, which is the essential update rule for Qs in all the algorithms that we're discussing, so like SARSA, semi-gradient SARSA, expected SARSA, Q learning. Okay, doesn't matter if they are on policy or off policy, they all belong to this class of critic-only algorithms. What we want to do now is to change the focus on another object, which is the policy. So we want to recenter our attention on the policy itself. Why is that? Well, first and foremost, because the policy actually is our original goal. We want to optimize over policies. Okay, so it is a little bit of an accident, an historical accident, that we start by discussing critic-only algorithms because they have been flourishing over the past years. But algorithms based on the policy are actually quite old, and they have been sort of neglected in favor of other algorithms for quite a while. But then lately they have just come back to the forefront because they have lots of nice properties, as we will see today. So what is the main idea of policy grid? So the idea is that we focus on policy. And since we want to deal with the situation where we have a large number of states and possibly actions, which typically happens, for instance, in robotics, we want to consider parameterized policies. Okay. So in general, our policy is a function which brings state action pairs into probabilities. Okay, so for each state, actually, there is one probability over actions. Okay, so it's quite a complex object, so we might want to reduce the dimensionality of these policies just by focusing on specific degrees of freedom of the policy. For instance, in robotics, like we did, like the example we did a few classes ago, you don't need to describe all the degrees of freedom that a robotic hand may have, because for that particular objective that you have, maybe not all these degrees of freedom are relevant. Okay, so depending on the task, you might want to strongly reduce the dimensionality of your policy, and therefore limit your search to a subset of policies. Okay, so the idea is pretty much the same as parameterizing the Q function or the value function in general, but now restricted to the focused on the notion of a parameterized policy. So one reason to do this is like I just said, is to avoid the curse of dimensionality. Okay, which is exactly what I just said, to reduce the dimensions over which you want to perform your optimization. And the second thing is that parameterizing a policy allows for randomized strategies. So what do I mean by that? I mean, if you run an algorithm like SARSA or Q-learning with function approximation, you will be focusing your attention a lot on policies that are nearly deterministic. Okay, so you pick the argmax of your Q, and then you allow for small exploration around that action. But as we will see shortly in a simple example, there are situations in which under partial observability, so if you don't have access to all the states properly, there are very simple examples which show that these kind of strategies which choose predominantly one action over the others might be strongly suboptimal. So in a general situation where there is partial observability, strongly unobservable system, randomized policy might be better than nearly deterministic policies. Okay, so these two are two fundamental reasons for which one might want to look into parameterized policies. Okay, to allow for these two benefits. So what is the idea? Well, the idea is that if we go back to our original definition, so what is our task is, you remember, we have to define this in terms of the expectation value. This is our goal, the long time return, which is the, as usual, the discounted sum or of rewards. Okay, so this object here is implicitly a function of the policy. Okay, so given a certain environment, it depends on the policy. So in fact, the point is that this is, if you assume that your policies belong to a set of parameterized policies, this is implicitly a function of the parameters of the policy. Okay, so depends on the parameters. So the idea behind these policy gradient methods is just to look directly at the objective function as a function of the parameters of the policy, and to perform gradient descent in this parameter. So trying to gradient ascent in this case. So we want to maximize our G, our goal, in directly independence of the parameter. In principle, not even passing through the notion of a value function. Okay. So this is in principle possible because our objective function can be made dependent directly on the policy. How to do it, we will see this in a second. But that's the general idea. Okay, is there any question about the conceptual strategy here? Do you get the point? Okay, very good. So let me start with very briefly with a motivating example. Which is the following one. This is a very simple task. It's actually, let me get the definitions in line. It's a very simple task in which there is there are just it's a very simple grid world, if you wish, in which there is a goal state here. Then there is there are 3 states, and the things you can do from these 3 states are the usual left-right actions. Okay, so you can actions are left and right, and if you are in this state and you try to go left, what happens is that you stay in place. Okay, so from each state you might want to go in this direction or the other, but if you do that, actually what happens in reality, okay, is that you stay in place. Okay. So remember that always actions express the intention of the decision maker. So in this case, if it's in the leftmost state, it wants to go to the left, but eventually it stays in place, which mathematically speaking, means that if you wish, let's label these states like 1, 2, and 3. So the probability of going to state S prime from state 1, given that I take action left, is just this one. So it's with probability 1, I get back to state 1, and there's nothing else that can happen. Okay. So in state 3, well, everything is okay. So if you decide to go to the left, you go to the left, and so on and so forth. Okay, so usual stuff. So let me depict in green the actual outcome of the actions you take. Okay. In the middle, in state 2, something weird happens in this particular example, is that if you want to go to the left, sorry, to the right, actually your actions are switched as an outcome. So you decide to go to the right, but in fact, what happens is that you go to the left. And the opposite. So in the center, your actions are switched. So you would like to go to the left, and instead you are sent to the right. First thing. Second thing is that states are not observable. Okay, so in this system, you don't know whether you are in state 1, 2, or 3. But still you want to go to the goal. Okay. And any other definition? There is a reward. Is equal to -1 for each step that does not take to the goal. Okay, so it's a terminal state problem in which you hop from one side to the other, and eventually you hit the goal, and the process terminates. And basically, you pay a penalty for every time that you spend in a tile which is not the goal one. Okay, it's a very simple Markov decision process, which is complicated by this switching of actions and by this lack of observability. Now, if you play with this simple system, you will realize that as a function of your, suppose that you do policy evaluation. Okay, so you just choose a policy. Remember, you do not observe states, so you can only decide the probability of going right or going left. That's the only thing that over which you can optimize. That's the only thing you can decide at every time. Should I go right or should I go left? And as a function of the probability of going right, okay, this is the probability that the action I am picking is right, and this goes from 0 to 1. And if you do this exercise, you will discover that so this would be 0 level, that your G as a function of this policy has a form like this. Okay, with a maximum somewhere here, which tells you that if you choose policies that are close to being either all to the right or all to the left, you perform very poorly. But if you choose a policy which is almost random, actually probabilities are not exactly 1/2, but it's just something around 60% to the right, then you get a much better performance. So this is a result of a combination of a non-trivial structure of the problem and the lack of observability. So this highlights the benefits of using parameterized policies, which allow you to find solutions for your parameters, which are somewhere in the middle of your probability distribution space, and not necessarily in the corners where near deterministic actions take place. So you may want to try to run algorithms like SARSA or Q-learning over this problem to see how they perform and what kind of problems they encounter. Okay, it's a useful exercise. Very good. By the way, this is exactly described in detail. This is example 13.1 of Sutton and Bartow book. And so you can find all the details of the definition in the book. And yeah, I encourage you to do the exercise. Okay, so at this point, I hope I sort of convinced you that it might be a good idea to look into this approach of trying to find out optimal policy directly. So the question is how to do it, okay? So remember, we have to, in a sense, the idea is that we want to identify if we can write the gradient of this G function, okay? So the first question, sorry. So question 1, how do I compute the gradient of my goal? Is there a compact expression that allows me to derive this? Okay, so how do I compute the gradient of the objective with respect to the policy parameter? First question. Second question. Suppose that I come up with an expression for the gradient, and we will, of course, shortly. This will depend on the model. This will depend on transition probability, okay? So still this expression will be heavily dependent on your knowledge of the model. So can we turn this gradient descent into a model free? So it's not descent because we want to optimize over G, so it's always ascent. So in other ways, another way to rephrase the question. So how do I estimate the gradient without access to the model? Okay, so this means that my mean rewards and my transition probabilities are unknown to the agent. Okay, so you see that there are these two questions that we have to provide an answer to before we can actually implement algorithms. So please, if you have any question or uncertainty or anything that you want to be clarified, just interrupt me at any time. So the answer to the first question is given by the policy gradient theorem. And the good news is that we already derived this. So all the calculations that we need, we have been already doing them when we were discussing how to derive the Bellman's equation. So in one of the derivations that you might remember, but I will point you exactly to the reference in the lecture. So when we discussed equation 10 in lecture 5, the version with annotations, which you can recover from the Slack channel, or you can look back at the lecture. You remember we went through a long calculation, which allowed us to write down explicitly exactly this object. That is the gradient with respect to something, okay? So in that case, we were differentiating exactly with respect to the components of the policy, but the same calculation goes through for any parameterization of the policy. And this tells me that the gradient of theta g can be written as the sum over states and actions. Eta s, let me write it, and then I will recall you what these objects are. The gradient of the policy itself only times the Q function. And this is. And this, the policy depends on the parameter theta. Okay, so the derivative here acts only on this thing. So let me recall you what these objects are. So this eta s is the on policy visiting times. Okay, so namely this is defined as the sum from 0 to infinity discounted of the probability that a state st I find myself in small cap s at time t. Okay, so after t steps, starting from an initial distribution, which I don't specify, it's something like we called, I think, row node or something. Starting from that initial distribution over states, after t steps, I find myself in state s. Accounting for discounting, which means that, as usual, I can implement this by a killing process in which I stop my process with probability 1 minus gamma at each step. Okay, so this is its definition, and as always, the value of a function, sorry, is defined through this expression that we have written an inordinate number of times. Okay, so again, the value here depends on the policy. All right, so this is our first important result. This is the policy gradient theorem, which, as you can see, it's quite interesting because if we knew what the model then is, so if we knew what the reward and transition probability are, we can compute quite straightforwardly the gradient. Okay, so if the model is known, then we can compute eta simply through its definition, which is identity matrix minus gamma p to the -1 times the initial distribution of row nodes. Okay, and this is a linear operation, and we could compute q from its definition. So we could actually compute, first of all, we could compute the value which is a row vector, which we can write as capital R T 1 minus gamma P minus 1. Okay, so this is just the usual recursion formula for value. So these two are linear operations, okay? So it might be a little bit cumbersome because there's an inversion, but you can use any technique from linear algebra to solve these two equations. And then the gradient of pi, this is always known. Okay, so it doesn't really matter whether you know the transition probabilities and the rewards, because these things you always have in your hands, because the agent decides what the parameterization of the policy is. So every time it receives the states and takes an actions, it knows exactly what the value of grad pi is. So combining these two things, you could compute exactly the gradient, and you could perform gradient descent. Okay, so this is exactly what we did actually as an algorithm when we were discussing policy iteration. Okay, so this is exactly what policy iteration does, only that this is now happening on a submanifold of the space of policies rather than in the full space. So we are following the gradient along a surface which is described by these parameters theta. Okay. So I encourage you to look back at the lecture files and 5 and 6 to refresh yourselves about what policy iteration is doing. So this kind of algorithm is doing something very similar, only on a parameterized surface. But we are not happy with that because we want to do this in the model-free case. So how do we do this? Okay, so here we have to look once again to this expression, and we're going to do a couple of very, very simple manipulations first, which tells me the first one that I do is the following one. I'm just going to write this as this is left unchanged. This is left unchanged. Okay, so these are dependent on the policy. And then I'm writing the gradient of pi, this term here. I'm just rewriting this as pi theta as times the gradient over theta of the logarithm of pi theta. So since the gradient of the logarithm is equal to the gradient of the function divided by the function, this is an exact identity. The only thing I have to require is that my approximation pi theta is everywhere strictly larger than 0. Otherwise, the logarithm doesn't make any sense. Okay. What I'm doing here is, in fact, I'm multiplying and dividing by the policy. Okay. So this is a simple algebraic step. But why is that important? Well, because now I can write this right-hand side as an expectation over trajectories, which is the same idea that we've been using when we were trying to learn the value of a function. And the idea is that now we can learn the value of the gradient by replacing these sums with expectation values. And here there are two objects over which we want to take expectations. So the first one is over states. Okay, so and here it's very easy, this first step, because this object here is nothing but the on-policy distribution of times. So if I generate trajectories according to this rule by which I kill processes with probability 1 minus gamma, this term above is exactly the expectation over the states, right, which are picked along this distribution, so the states which are generated naturally by this evolution. Let me write this in capital letters so to be clear that this is a random quantity. So this is going to be the expectation of Q pi with a capital S. There still is a sum over A here, okay, for the moment. And then I have pi theta A capital S times grad theta log pi theta S. So I got rid of the first sum over this distribution and replaced it by an estimate, an expectation value. And then I take the second step, because I can take now, there is a policy here. So this sum over actions which are weighted by their probabilities is an expectation value itself. So this is also equal to the expectation value over states taken from this distribution eta and over actions taken according to the policy pi theta. Of what? Of Q pi. Now, over a certain pair of states and actions that are sampled times the gradient of theta of log pi. So what is the first thing that we have accomplished here is that we have removed in part our dependence on the model, because now almost we can give up the knowledge of the model, because we are just sampling actions and states according to how they are generated by a model which could be still unknown. Why do I say almost? Because still here we have the Q function, which we don't know. Okay? And in its belly, it also depends on the model. So we have to take a final step in this direction. And we would like to replace this Q function with something that we know just from the trajectories of our system. And here, there are several directions in which we can go from here. Okay, so the key step that is left to say is just to remove modal dependence in Q pi. Okay, that is, we want to turn this object into something which we can sample rather than compute from the model. And there are different ways in which different directions in which we can proceed. So the first one is to use Monte Carlo. So what is the idea? The idea is that Q pi from a given state and action can be replaced by its stochastic version, which is nothing but the sum over from t going to 0 to infinity of gamma t of the rewards in the future, starting from a specific state and action that we are picking along the trajectory. So imagine that you have a stream of data. Okay, our usual stream of data that comes in which you have a state 0, action 0, reward 1, state 1, action 1, reward 2, etc., etc., etc. Then you have a reward t plus 1. So it's a state, it's t action. Sorry, this up. So we have state t, action t, reward t plus 1. Let's see. T+1, etc., etc. Okay, so you have all this long stream of data, and at every time that you're sitting at a certain state action pair, okay, which corresponds to these two state and action that you're visiting, you just look from that point onwards. So imagine you have an infinitely long stream of data, and you can compute this quantity starting from this pair. And then you move one step ahead and you repeat the same thing, and so on and so forth. So you are using the Monte Carlo approach. Or another way of saying that is that suppose you're simulating your system with your policy. So you generate a new state action pair, and then you just spawn a side simulation which samples all the future rewards starting from that, and therefore returns you your estimate of the goal. Okay, so this object here is exactly the Monte Carlo estimator of G. So if you combine these things together, the final result is that you can write down your average gradient exactly as an estimate of the future rewards discounted starting from a certain time t times the gradient over theta of the logarithm of your policy pi taken in action at and state st. So at every time step of your trajectory, just look forward from that trajectory, from that point into your trajectory. You construct your stochastic estimate, which is unbiased because it's Monte Carlo. You multiply times this term here. Okay. And then you have your estimate of the gradient. So this object here is your estimate of the gradient, which is defined like a GT. So it's the estimate of G times theta. Now everything has become computable without having ever to invoke the knowledge of the model. Of course, computing this G hat estimator is in general very expensive, and it's prone to large variance, as all Monte Carlo methods suffer. I mean, all Monte Carlo methods suffer from this problem. Okay. So this algorithm in this form goes under the name of reinforce, introduced by Williams in '92. Okay. And so how does this this algorithm work? It's worth writing down the pseudocode for this. So as input, you have a differentiable parameterized policy. Pi theta of actions and state. So this provides your mapping from your low dimensional parameter space to your high dimensional set of actions for each state. Then you have as parameters, you have some learning rates, alpha, and then you initialize your theta parameters somehow, okay? For instance, you may want to set them all to 0, it depends, okay? And then you do a loop for each episode. In which you generate a trajectory okay, which is this string of states, actions, rewards, states, actions, new rewards, and so on and so forth, okay, until a certain time capital T, okay. And you do this using your policy pi theta, okay. Then for each step of the episode, at each step of the episode, so this is a loop over steps, if you wish. You compute your estimate of the future rewards by summing from that time to the final time over, say, kappa minus t times the rewards at time kappa plus 1. Okay, so this is how from your sequence of data you construct at any given time what your trajectory gives you as reward from that time to the end of the string, which of course should be sufficiently long. And then given that, you can update, this is the important part, you update the policy by doing stochastic gradient descent. Okay, so you take a step in the direction of the gradient. But what is your estimate of the gradient? But well, you have it here. This is your estimate of the gradient, and you plug that here. So you have alpha g grad log pi at st. Until your episode is finished, you arrive at time capital T, and then you restart with another episode, and so on and so forth. So your parameters will migrate, will move around, and will lead you to a value parameters which tries to optimize this. For instance, you may want to try this algorithm with the example that I gave you earlier. And you should be able to see that if you parameterize the policy somehow, okay, you should be able to find out that the optimum for the switched actions one-dimensional grid world leads you to a policy which is randomized with a probability of going right around 60%. So this is a quite straightforward approach, and this is an example of an algorithm which is now called actor only. This has to be constructed, this has to be contrasted with the critic only algorithm. In the critic only algorithm, the value function was central and the policy was a derived object. Here, only the policy exists. You see, we did never mention the notion of value function up until here. Everything comes from just estimating from trajectories in the most straightforward way by Monte Carlo and using the policy. So everything now is centered around the policy. So this is the polar opposite of what critic-only algorithms do. And you will not be surprised to imagine that, and this we will do in the second half of the lecture, you can take the two worlds together and mix them together to produce a new class of algorithms which are called actor-critic algorithms, which inherit some of the benefits of the two. And so we will be able to sort of mix in the idea of optimizing over policy together with the idea of temporal difference learning to estimate the Q function. And when we combine these two together, we get to our actor-critic algorithms, which are extremely powerful and widely used nowadays. But before we go there, there's one thing that we can still do in this setting of the reinforced algorithm, or if you wish, the actor-only, pure actor algorithm. So in general, this Monte Carlo estimation is painful because if gamma is close to 1, this means that you need to have very long trajectories, because otherwise this sum will be always cut off by the finite horizon capital T of your data. Okay, but there's one situation where this problem does not arise, and it's the situation of bandits. Okay, so the situations in which these algorithms are good is when gamma small, for instance, and this is the example of yeah, so gamma small or terminal state reached quickly. So in both cases, the episodes are short, so you can use this very effectively because you will have to run episodes over 2, 3, 4, 10 steps, and this makes the algorithm quite quick. Or, of course, as a limit, bandit problems, where you might remember you can set basically gamma equal to 0 because the rewards are independent. So this is the stochastic setting. So every time that you flip a coin, you get a head or a tail, and there's no correlation between outcomes, and therefore you can safely set gamma equal to 0. You have to solve a problem of immediate reward over a certain series of agents. So a good question is, what do these algorithms become for bandits? Okay. And so here I will just give you very quickly one example. So for instance, suppose you have 2 bandits. So the actions are just 1 or 2. Remember that there is just one state. So basically, this is a stateless problem. So what does this imply? Well, this implies that your estimate. So first you have to introduce a policy. So let's go one step at a time. Okay. So we have to define our parameterized policy of the actions 1 and 2. So there are just 2 actions. So since the probabilities must sum to 1, okay, I just have pi theta of 1 and pi theta of 2, and these 2 must sum to 1. So pi theta of 2 is equal to 1 minus pi theta of 1, of course. So which means that I just need one parameter to specify this policy. And for instance, I could use a logistic, what is called the logistic Bernoulli unit. Which is, if you want to think about it, you could think about this as just as a single artificial neuron. So you could define this as pi theta of 1, just like 1 over 1 plus exponential of minus theta. So you have a parameter theta which runs over the real axis, and you have an expression which looks like more or less like this. It's sigmoidal form for your policy. So large theta would correspond to policies which choose action 1 with probability close to 1, and negative parameters corresponds to a preference towards action 2. So how does reinforce look for this choice of parameterization? Okay, then you just have to do one thing. So for bandits, your estimate of G is just the reward. Okay, so there's no future, it's just what you get when you play that action. And so starting from state is always the same. So your GT is nothing but the action, the reward you get when you play action at time, action A, T, at time T. It's just the plain random reward. And what is grad log pi of action AT? Okay, so this is a very simple, straightforward calculation, which you can do by yourselves. But you can easily realize that by taking the derivatives, you can find the closed expression for this object, which I'm going to report here for you, and you can check separately, is that this thing is going to be either pi 2 for if action is 1, or minus pi 1 if the action is 2. Okay. It's just a straightforward derivation exercise. And therefore, if you combine these two objects together, you know how to improve your theta parameter. So what is happening in this algorithm? Let's have a look. If your reward is large, if you pick action, let's say, if you pick action 1 here, and your reward was large, this will make a large step in the direction of 1. It will increase your probability of taking that action. On the contrary, if your reward was not very large, or maybe negative, you will take a step in the other direction. So depending on what kind of rewards you get, you will tend to move a little bit to the right or a little bit to the left. And this will make you drift in this theta parameter. Okay, so this is what is also called the gradient bandit algorithm in Sutton and Barton. One of the many forms by which you can. So of course, all that's happening here can take several forms depending on how you choose the parameterization, etc. Okay, so this will be a problem that we will discuss also separately. All right, very good. So what are the problems of this algorithm, which I have to highlight from the beginning? So one of the problems is that, and it's the major one actually, which I want to discuss here, is that this algorithm behaves differently if your rewards are, for instance, suppose your rewards are, the reward for 1 is 100 plus some Gaussian noise with 0 mean and variance 1. And your reward 2 is 101 plus the same Gaussian. Okay, so this is problem 1. And problem 2 is your rewards are 0 plus a Gaussian of the same 0 mean and variance, and 1 plus a Gaussian. So are these two problems different from the viewpoint of decision making? No. It's just that there is an offset in the definition of the rewards. But the difference between what you get from action 1 and action 2 is exactly the same. So the optimal policy is the same. It's just an overall offsetting rewards. However, if you look at this algorithm here, as it is, this estimate of the gradient is sensitive to the absolute value of the gain. So for problem 1, you will have large fluctuations of the gradient because you're multiplying everything times 100 in your estimate. So your difference will be submerged by this offset. So the solution to this problem is actually quite simple, okay? Because what you have to realize is that you can actually write down an improved version of the, so improved policy gradient with the use of a baseline. So what is the idea in general? Remember that we started from this, sorry, not J, the notation that I used is G. So the gradient of G is the sum over states and actions of eta S, Q S A, red by E S. Now, let's consider a variant, okay? An object which we call, let's call it gradient prime, okay? Which I define as sum over states and actions of eta S. And then I subtract an object here, which is called the baseline. Which only depends on the states. It does not depend on actions. So let's see what happens to this other definition of the gradient. So what does happen is that if I split this into two terms, I have the first part, which comes from distributing this difference over the gradient. So the first part is the pure grad G. And then I have minus sum over states. And then I have eta of S, B of S. And then I have sum over actions of the gradient of the policy. Okay. I'm just using simple algebra. But now here the important things happens because I can write the sum of the gradients as the gradients of the sum. But the policies are probability distributions over actions. So these are normalized. So this object here is equal to 1. So and the gradient of 1 is 0. So all this part here, which was depending on the baseline, vanishes. So as a result, I just have that the gradient that I defined with the baseline is exactly the same of the gradient. So what I can do now is to use this freedom that I have to define a baseline to remove the offset here. Okay. So in this particular case for bandits, what I can do is to replace my rewards with the rewards minus some baseline, which for instance could be the average reward that I get. Okay, so as I experience rewards, I account for the average reward. And this will remove all my dependency on the offset so that I am able to find an algorithm which has smaller variance. So the gradients which are estimated with the baseline may have a lower variance than the gradients estimated without the baseline. Okay, so you can choose whatever baseline. So the choice of the baseline here One typical choice is to choose the baseline as the value function itself. Okay. But there are other ones. So, for instance, you could choose B so as to minimize the expected value of the square of your gradient, which means that you minimize variance of the estimate of grad G. So this is the first one. The first choice does not correspond to the second one. So the first choice is a choice which means that you're trying to equalize your Q function with your value function. Okay, so you try to reason in terms of relative advantage, and in fact, this is what gives to advantage. Technically speaking, the advantage is the difference between the Q function and the value function. Or you can reason in statistical terms and say, I want to choose a baseline which reduces the variance of my estimate, which leads you to other expressions that I'm not writing down, which are a little bit more complex. And these two things in general are different. These are two different ways of choosing the baselines. Both of them work, and both of them have their own merits and difficulties. Okay. We've been quite long on this first half. So are there any questions? Clarifications? Okay. If not, let's take a well-deserved break. Is there a question from anyone? No.
I have a small question. Sorry. In the algorithm, the small t there is per step, right?
The pseudocode here, yeah.
The small t.
Sorry?
The small t is like t is equal to 1 is the first step. Here, loop over steps.
Yeah, so this you repeat at every step. So you start with t equals 0.
Yeah.
And then you start here and at this point here, and then you look at all the trajectory.
Yeah.
Sum up discounting. Okay. And then you use this to compute your.
But when we do this, how do we choose the big T?
No, this is something that comes from your problem. So if it's a problem with the terminal state, it's just chosen randomly by the process itself. So you have a string which terminates when you reach your goal. If it's a task that does not end, it depends on which data you have at your disposal. Okay, it's something that if you can choose, you should choose it in order to be at least 1 over 1 minus gamma, because that's the typical horizon of your process. Otherwise, your sums here will be truncated before you can actually accumulate the object. So your estimates will not be unbiased.
So it depends on this pi theta, on how you.
It depends on the theta.
On the pi theta.
Yes, it depends on the policy. Yeah, right. It depends on the horizon and on the policy itself. But if you go long enough, this sum here will be killed off by these geometrically decreasing factors anyway. Okay, so you will have if you have many times, like many times more than 1 over 1 minus gamma, then you will have many contributions, and then maybe just the final tip of your string will not be long enough, so you can forget about it. But it's extremely expensive when you get gamma close to 1. In terms of
so the gamma is also chosen by you?
The gamma is a part of the problem.
Yeah.
It's your objective. It's something that you have decided at the beginning. Some problems make sense with the gamma close to zero. Some others you need a long gamma. If you need a long gamma, the bottom line is that you don't use this algorithm. You don't use Monte Carlo. You will use the algorithm that we will introduce in the next section.
Okay. Thank you.
Any other question? No? Okay, good. So let's take a break and we start again at 10:25. Okay. So let's resume the discussion and let's just recapitulate the kind of steps that we took so far in order to introduce the next class of algorithms, which combines ideas from actor only and critic only and merge them together in this new class of algorithms, which are called actor-critic algorithms. So everything starts from the policy gradient theorems, which once more, I'm writing this for you, starts from this expression, the previous definitions. And then the basic step, first step is that you can use a baseline. And you can replace this expression with some difference of your Q function times some object as yet unspecified. And then let's see what happens if you choose the value as a baseline. This becomes okay. So this series of steps is quite straightforward. We've been manipulating our policy gradient theorem in order to write it in this way. And then we take yet another step, which is still exact. We replace here the definition of Q. So sum over S prime, P of S prime, SA, over R SA S prime plus gamma V S prime minus V of S, all this times grad theta. So let me yes, and I can remove this bracket here because it's not necessary. Okay, so far I've been just using this property that the baseline doesn't affect the gradient and choosing specifically the value function as a baseline. This allows me to write this prefactor here as the advantage function, which is the difference between the value for that action with respect to the average value of all actions, Q minus V. And now once I am in this situation, okay, I can do rewrite this object in this form, which is the expectation of what? I do the trick of rewriting this in terms of the logarithm. So this would be the expectation of the reward. Okay, this term here, the random reward, plus gamma, the value of the policy in ST plus 1, minus the value of the policy in ST, times gradient theta of the logarithm of pi of kt st. So far, I've been just repeating what we did earlier with a specific choice of the baseline. But as before, we have the problem that this value function v pi, which appears here, is not known. Would need to be evaluated from the model, but we don't know the model. So rather than doing Monte Carlo, that is to compute an unbiased estimate of my value function by using my trajectories, I can use bootstrapping. That is, I replace my value function, my true value function for that policy, with some approximation, which might depend on some other parameters W. So here you see that's exactly the point where we can merge policy gradient with the temporal difference learning, because we are going to replace our value function by some approximation, and we are going to use some algorithm from temporal difference learning to learn this approximation. And so at the same step, we are going to improve the policy by moving in our theta parameter space, and improve our approximation by moving in the W space. Okay. So if we go that, now I have to put not more inequality because I'm doing an approximation, but if the approximation is good, I expect this to be valid. This is sort of sloppily the expectation of what? Of RT plus 1 plus gamma, the approximation for at the state as t plus 1 parameters wt minus v of st. Let's just use w for the moment without the time index. Okay, all of this multiplied times my gradient theta of the log. Now, if I keep myself temporal difference learning with temporal difference learning for the parameters of the value, then I have a complete algorithm which goes under the name of actor critic. Okay. So I am using an approximation for the value to obtain this object here, which now you will recognize exactly as the temporal difference error. So this is the place where temporal difference learning comes into place. The prefactor that appears in the estimation of the gradient is exactly the temporal difference error itself. So this means that we have an approximate estimate of the gradient, which is going to be biased because now the approximation induces a bias, the approximation for the value function. So I'm going to have an estimate of the gradient, which is just the temporal difference error times the gradient of theta of log pi. So the idea is that we have stochastic gradient ascent in theta plus semi-gradient TD learning in W. So we have two sets of parameters for the policy, parameters for the value function. We learn an approximation for the value function, and we try to move our policy towards better performances by following the gradient. So when we combine all this together, we get the template for the actor critic algorithm, which has a pseudocode that reads as follows. So you have as an input the policy parameterization by theta, which has to be differentiable and positive. Okay, otherwise you cannot perform derivatives, and you cannot perform derivatives of logarithms in particular. You cannot take logarithms. Then you have a value parameterization v, small v of s, and parameters w. Let's put ahead here. Then parameters. Okay, you have two parameters, one to learn the policy, and one to learn the value parameters. Both must be positive, and as always, they should be scheduled accordingly if you want this algorithm to converge to something with probability 1, and whether this something is optimal or not depends on the approximation. And then you initialize parameters, weights. Okay, so these are called weights. It could be a neural network. Okay, so this theta could be parameters of a neural network, both for pi and for w, and for v. This could be two different neural networks. This could be one large neural network which combines the parameters theta and w together. So there are different architectures for approximation. You could use a neural network for pi and a linear approximation for v, or you could use hard choices for the parameterization because you have some insight about how the policies should look like and how the values should look like. All the complexity and richness of choices for your approximations are available. Of course, as long as you use non-linear parameterization, and for policies, all of them will be non-linear, you might end up in local optima. This is always a possibility, so you have to be careful. Nevertheless, if you accept all these caveats, then you have the usual couple of loops for your pseudocode. You can loop over episodes, and then you loop over, you initialize your state S, your initial state, and then you loop over time until the end of the episode. And what you do is the following. You pick an action according to your policy with your current parameters and at your current state. Okay, so you have a state, you have the parameter, you can extract a random action from your distribution. Then, as always, you take action A and observe reward and the new state. That's the usual routine. Then you construct the temporal difference error. You take R plus gamma, your estimate at the current parameter values. This is S prime. This is the usual temporal difference error for value learning. And now you use this temporal difference error twice. One to update the value estimate itself, and the other one to update the policy. So the temporal difference error is present both here when you take the gradient of the policy, then also present, of course, when you have to do semi-gradient learning for the value. Explicitly, your new parameters W are just W plus alpha W, the learning rate for W, times the temporal difference error times the gradient with respect to the parameters of V. This is temporal difference semi-gradient learning with approximation. We did this 2 or 3 lectures ago. Then you improve on your parameters by again using the same temporal difference error, but now you multiply this with grad log pi. So you see this structure which repeats itself. You have temporal difference error times eligibility. It's always like this. And you're using the same temporal difference error to improve both aspects of your decision making. And then you call your new state as the old state, and you repeat. You close the loop. And back you are. And then you repeat over episodes until you reach some convergence criteria. Okay. So this kind of algorithm can come in different flavors. You can add eligibility traces in order to keep track of memory. You can do many variations on the theme. You can use whatever kind of approximation you like. So this is the core algorithm which describes this combination of temporal difference learning and gradient ascent, stochastic gradient ascent on policy parameters. So graphically, what does this mean with respect to the diagram we had for the critic only? So let's go back again to our usual interface. So here, again, there is a critic which receives rewards and states. It has an approximation for V. Okay, so inside the critic, there is our approximation for the value function. And by combining rewards and states and the current estimate, it produces a temporal difference error, which is fed back into the critic. And so far, this would be a critic-only algorithm. Now, what changes here is that this arrow goes also to the actor, which is the new box which is happening, which is appearing here. So the temporal difference error is also fed to the actor. And the actor contains the policy and updates it thanks to the temporal difference error. And this then results into an action taken. Okay, so there are these two centers for decision making, which are the actor and the critic, and they communicate to each other. The critic evaluates the current policy, so it says how far off the approximation is from the actual policy and how large is the discrepancy, and then communicates this discrepancy to the actor, which tries to use this information to optimize the policy towards its objective. Okay. So this is a very rich architecture, and we will see examples of this in the tutorial next Friday. Fine. I would like to use the final minutes of this lecture to sort of list many possible directions in which you can expand and improve over these Arthropetic algorithms. Okay, so extensions and improvements. So there is a large number of variations on the theme of policy gradient algorithms, which include different ways of approximating objects depending on what you do, different baselines, different kind of implementation of the neural networks that approximate your policy and your value function. I will not discuss all these aspects, which are nevertheless very important in obtaining practical results in difficult problems. What I want to focus the most on these last minutes is one particular extension, which goes under the name of natural actor-critic algorithms. So one limitation of these gradient approaches is that clearly the gradient of your performance depends on the choice of the parameterization. So if you choose different parameterization, you will get different prefactors in your gradient. Okay, so this can affect learning because your actual numbers that you put in front of your improvement change the dynamics of your learning algorithm. Okay, so one important aspect is that so-called vanilla gradients, okay, which are the ones that we describe here, depend on parameterization. And another issue, which is not totally unrelated, but let's discuss it independently, is that gradient descent can be unsafe. So vanilla gradient descent. So by vanilla, I means that just the simplest version that I gave you until today, so without any decoration or modification. So what do I mean by gradient descent can be unsafe? So let's think about an everyday experience. Suppose you're hiking on a mountain, and I mean, you made it to the top, and now it's time to go back to your starting point. So do you use gradient descent to go back to your starting point when you hike? Certainly, it's a fast way to go to the target. But the problem is that if you make a step off a path, you might as well fall off a cliff. Okay. So how do we make sense of this procedure of getting down the gradient in a safe and controlled way? Okay, so this was just a motivating example, but if you think in detail, what you're actually doing when you're walking down a steep trail in mountain is that you want to go down, but you want to keep the length of your step under control. Okay, so you don't want to make a step that will bring you 100 meters below in a cliff. You want to go down, but you want to keep your steps always to be 1 meter. Maybe if the ground is very difficult, you maybe want to make a step of 20 centimeters, just putting 1 foot in front of the other, 1 foot in front of the other, right? So is there a way of formalizing this notion of going down, but controlling the length of the steps that we make? Okay. So the intuitive idea is that I have to trade off my willingness to go down as fast as possible with some condition that limits the length of the step that I want to take. Okay? So this is what, in a sense, gradient descent does, because you might remember it combines, it tries to weigh in two different ways the need to go down the gradient and the need to make small steps. So recall that gradient descent of a function f can be written as a sequence of approximation or steps, in which the new step is the previous step minus some learning rate times the gradient of f evaluated in x in k. Okay, so this is what gradient descent does. You evaluate the gradient and you make a step in that direction. You can rewrite this problem in the following form. You want to find the mean, sorry, not the maximum, but the minimum. The minimum over all x prime, such that grad f in x times, where x is your xk, grad f times x minus x prime minus xk, with some parameter alpha in front, and then you put a penalty. So you want to go down the gradient, so the gradient goes yes. Plus some penalty, which is the distance, the square distance between x prime and xk. So if you minimize this quantity, which is just a quadratic function in the coordinates, so if you take the derivatives with respect to x prime and try to find the minimum, well, you will realize that this is exactly xk plus 1. So here you're expressing gradient descent is exactly as a compromise between going down but not making too large steps. And this trade-off parameter between these two requests is exactly the learning rate. So the point here is that if we do gradient descent in policy space, basically we are using an Euclidean distance. But is this the right distance to use for probability distributions? Isn't there a better choice to measure distance between probabilities? And the natural idea is to replace this Euclidean distance. So if we search over policies, we should replace the L2 norm with the Kullback-Leibler divergence between probabilities. So this is the natural notion of a distance between probabilities. So if you do that in a way that I will not show, but it's a couple of lines of calculation, what you're actually doing is that you're replacing your gradient here for small alpha. You're replacing the gradient with another object, which is called the natural gradient. This natural gradient is just a sort of a deformed way of your actual gradient. In fact, you can write down an explicit form for this natural gradient, which again, I'm not giving to you, but it's I will point you to papers that discuss this in detail. I will upload them on Slack. So the natural gradient is actually an object which is composed of the ordinary gradient. Okay, so this is a vector. So this is an operator vector. So this is the gradient with respect to any parameter theta that you have. So it's a vector of derivatives. And this object here, this f here, is the Fisher information matrix. Which is connected to the Kullback-Leibler divergence, because the Kullback-Leibler divergence between two probability distributions parameterized by two parameters could be any probability distributions. When the parameters are closed, this is approximately 1/2 times theta prime minus theta transpose Fisher matrix theta prime minus theta. So said in other words, F is a metric. So it's a notion of distance, of differential distance in the space of parameters. And this natural gradient is a sort of covariant gradient, for those of you who ever heard about this thing. It's a gradient which takes into account the local geometry of the space of parameters. So this is where Arthropetic algorithms meet a whole field of information theory, which is called information geometry. Okay, so you just need to know that there is this connection. But what is most important is that these natural arthropetic algorithms, which work exactly in the same way, but take different definitions of derivatives. Okay, so in natural Arthrocritic, it's just Arthrocritic replacing the gradient with the natural gradient. Okay? You don't have to change any line of the algorithm. Just when you take the derivative to compute the gradient of the policy only, okay? Because the values live in the usual quadratic space. The value error is defined in terms of an Euclidean norm, but the parameters of the policy live in the space of probabilities. So if you replace the gradients with respect to theta with the natural gradients, you get your natural Arthropetic algorithms. And these algorithms have been particularly impressive in learning robotic tasks. So that's why they are very important on one side. And they are also very important because they make an important connection with game theory that we will explore tomorrow. Okay, so tomorrow we will review shortly again this natural Arthropetic at the point when we have to discuss multi-agent algorithms. Okay, so I will upload the reference on Slack, but for those of you who just see the lecture, the paper I will be referring to is called the Natural Arthropetic Algorithms. And let me just check because I don't want to miss any of the authors. I remember just 2 of them. I will make sure that I quote all of them. So allow me 1 second to dig it out. Match. Okay. Okay. Natural Arthrocritic, no, without algorithms. And this is a paper by a review by Peters, Vijay Kumar, and shall 2005. Okay. So this is a very interesting paper, which is self-contained and explains lots of with examples, the crucial aspects of introducing this different notion of gradient. All right. So I think we've come full circle. If there are any questions, I'm happy to take them. Okay. If not, you know that you can always. Oh yes, please.
Hello, I have a question about the exam, the project.
Oh, just a second, then I'll just stop the sharing and the recording, and this.
Okay.
Separate.